So what I'm going to do is I'm going to talk a bit about work that I've done, which is what Pam's heard a bit about before. But I'm going to kind of talk a little bit about some of the criticisms of that work as well. So actually sort of what people have said about it and where they've picked up on critiques of it, which has been quite interesting. And then I'm going to talk about, I might as well show my title slide, actually my structure slide. Then I'm going to talk a little bit about the news you might have seen about last year about the source of the altar stone at Stonehenge being linked to northeast Scotland. And I'll try and give very much a personal view on that and what I guess I think about that study and what I think are some of the issues with that. So split it into three bits really. I'm going to start off by giving you a bit of context about Stonehenge because that's always useful, tell you about what the stones are at Stonehenge and tell you a little bit about the history. Then I'll show a little bit about the work that we've done on the sarsen megaliths. That's really where my work has come in. Including, this is something Pam hasn't seen. Sorry, I'm picking on you, Pam, aren't I? Something that Pam hasn't seen before, which is a really lovely video from the 1950s of work being undertaken at Stonehenge, which I hope you'll enjoy if we get it to work. And then I'll talk a bit about the altar stone, and then we've got time for questions afterwards. So that's the sort of broad structure. So we all know a bit about Stonehenge, don't we? I guess. So I'm just going to give you a little bit of broader context, but I'm going to focus mainly on the stones and a little bit about the history of the site. Now, I think when most people, I'm guessing most people have been to Stonehenge, and most people probably made a beeline straight for the stones and probably ignored the rest of the monument. But actually, Stonehenge is a lot more than just the stone circle. So the map on the right shows the layout of the whole site. And if I can get the pointer to work, you can hopefully see you've got this kind of bank and ditch structure around the outside. So there's a ditch that runs right the way around the monument with a bank on the inside and on the outside. Obviously you've got the stone circle in the centre. You've got another bank structure called the avenue that heads off to the northeast. And then as well as the stones in the middle, you've also got a number of other sarsens. The station stones, I'll say more about those in a minute, which are sarsen stones. One there today, one was there, one's there, one was missing down here. But they basically mark out a kind of a rectangle around the monument. And then you've got other stones like the heel stone and the slaughter stone that kind of mark the northeast entrance to the monument. If we zoom in on the circle, because that's the bit that I'm going to talk a little bit more about, you can see the stone arrangements in a little bit more detail. So my interest is largely in the sarsen, so that's the red and the kind of beige ones. The beige ones are just stones that have fallen over. But hopefully what you can see is probably the most kind of iconic part of Stonehenge, which is the outer stone sarsen circle that would have gone probably right the way round. Well, no, it definitely went right the way round. The only thing we don't know is whether the lintel stones that sit on top of the uprights necessarily went all the way round, but they probably did. And then in the middle of that, you've got a horseshoe-shaped arrangement of sarsens, and these are the biggest sarsens on the site. These are arranged as what are called trilithons. So these are where you've got two uprights of stone and then a lintel across the top, and there are 5 of those. And I say these are the really, really big stones. So I'm just going to check my notes. So stone 56, which is this one here, which was the kind of the central grand trilithon, is an estimated length of 9.1 meters. So that's 30 foot, I guess, in old money. That's quite a big sarsen stone. Stone number 54 down here is probably the thickest. It's not quite as tall as stone 56, but it's got an estimated above ground weight of just over 30 tons. So these aren't trivial bits of rock, I guess is the point I'm trying to make here. So you've got the sarsen circle, you've got the sarsen horseshoe, the trilithon horseshoe. You've then also got blue stones. So there's a variety of other stones, which are the smaller stones. These are the ones that the majority, they're a mixture of lithologies. There's a whole range of different kinds of igneous rock, mainly dolerites. But these are the ones that the majority of them are thought to have come from West Wales, so the Preseli Hills in Pembrokeshire. They form a circle. There's also a horseshoe-shaped arrangement of blue stones in the middle of the monument as well. And then I'll talk about this later on. The altar stone sits in the middle, which is a sandstone megalith. But you've got this kind of overall arrangement. Key things, I'll check my notes there, key things I meant to mention. So if all of the sarsens were there, you would originally have had around about 80 stones. There are 52 left today. So we've lost 28 sarsens over history, broken up, who knows where they are. There's 52 remaining today. And there were, I don't remember the exact number of bluestones that are estimated to have been on site, but there's a lot more of those. But they're generally the much smaller stones. I'm not going to talk much about the detail of the bluestones other than talking about the altar stone in a little bit. I guess when I was asked to talk about Stonehenge, there's so much you could talk about, you end up having to be a bit selective. So apologies if anybody wants, if we've got some die-hard Dollarite fans here. Sorry. Okay, but that's where we are today. So we're looking at a monument that has quite a complex structure. Very important thing to remember, though, is this is basically just a snapshot of what's there now. And Stonehenge actually has quite a long history of formation. I'll just put this diagram up from the English Heritage website. We know that Stonehenge was constructed, it had probably 5 phases of development over its history. And we know that by modelling work that's been done looking at radiocarbon ages associated with the monument. So we can pick up very clearly that there are 5 phases of development. It just shows the first 3 here. I'm not too worried about the 4th and 5th because they involve relatively minor changes to the monument. But the history of the site goes back to at least 3000 BC. And the earliest evidence, so there are some elements of the site like there's a barrow, which would be just up in here, and the heel stone, which could be older than 3000 BC. But the first real thing that we see happening at Stonehenge is the construction of the bank and ditch structure. So that's about 100 metres across there, entrances in the northeast and in the south. Inside that, we've got a ring of holes. There's 56 of them, which are now known as the Albury holes. And for a long time, they were thought to have held wooden posts. There's some arguments maybe they held stones. Bit of debate about that still. But what we do know about the Albury holes is, and the ditches as well, is that these were places where cremations were buried. So within the Albury holes and within the ditch, there's been identified 64 cremations. Some of those cremated remains are mixed remains of more than one person. And I think the estimates are there's probably about 150 individuals their cremated remains are present at Stonehenge. So during the kind of late Neolithic, this was the biggest graveyard, probably in Europe actually, of a single site. So we've got this is almost like phase 1, if you want to think of it in that way. Where the bit that I guess we're all more interested in happens is about 2500 BC, and that's when the stones arrive on site. And all of the bluestones and all of the sarsen stones, we don't know exactly how long it took, but they all arrived in a reasonably tight window of time. And I'll say a bit more about that a little bit later on. So this was some kind of very large effort in a relatively focused period of time to construct a stone monument within this henge structure. So you've got the arrangement of the sarsen circles, the arrangement of the horseshoe of trilithons in the middle. The bluestones also arrived. The station stones are put up, and much of the monument was in place by about 2500 BC. So Stonehenge we see today mostly was in situ by then. About 300 years, there was a bit later, there was a bit of moving around of the bluestones. So that you'll notice there's no horseshoe shape in the middle there. The horseshoe was created. There was a bit of movement around of the bluestones in the middle. They didn't move the sarsens. But the other thing that happened around about 2200 BC was that the avenue was constructed. So this is a big banked kind of, it's not a road, but a sort of a pathway that links Stonehenge to the River Avon, and it's got a bank on either side of it. But basically, by the time we hit 2200 BC, we're pretty much looking at the configuration of the monument as it stands today. And as I say, there's a couple of things that happened subsequently, but nothing really affecting the major arrangement of stones. The image at the bottom shows kind of the arrangement of the monument if you were standing at the heel stone up here looking southwestwards. So you'd be looking right into the horseshoe shape at the middle of the monument. Now, there's a lot of debate about exactly what Stonehenge was built for, and I'm not going to say too much about that. There's arguments it was a place to venerate the dead. That comes through the idea of all these cremations that have been identified. Maybe it was a place for the dead and remembrance and worship of the dead. There's also suggestions that it's maybe a place of healing, and it was almost like a place where if you were ill or sick, you came along to be healed. There's been suggestions that it's a solar calendar. There's all sorts of other suggestions. But what we can be fairly confident about was that the people who built it knew quite a lot about the movement of the sun. So you probably all heard about the fact you've got this very nice symmetrical alignment. If you look at the plan of Stonehenge, it's got mirror symmetry basically on a kind of a northeast southwest axis. Even the station stones line up perfectly. And a lot of people, it's quite interesting, we all get really excited, or certain people get really excited about being at Stonehenge for sunrise on the summer solstice. Probably it wasn't designed for that. It was actually the alignment with the midwinter sunset was the critical one, probably marking the kind of end of the year rather than celebrating the middle of the summer. And, you know, this is kind of borne out by the fact that, you know, you're looking into the horseshoe, and there have been studies of the surface of the stones here, and they're much more carefully dressed, cleaned up on the inside of that horseshoe shape arrangement than they are around the outside. So it's almost though it was built to look into it in that direction, and that lines up with the midwinter sunset. You may not know as much, there's also a lunar alignment at Stonehenge, which you may not be aware of. There's work going on at the moment looking at this, but without going into too much detail, the moon doesn't always rise in exactly the same place. Just like the sun, you see the sun, the rising point of the sun moving across the horizon. Moonrise also shifts. Moonrise goes over, and I forget how many year cycle it is, but when it's at its most southernmost rise, if you were standing looking at this station stone, looking towards that station stone, you'd be looking absolutely bang on at the edge of the stones there, and the moon would be rising on the horizon over here. So there's arguments that this was not only a lunar, not only a solar, place of worship of some sort, but also that there was some link into lunar cycles in there as well. But there's, as I say, there's work going on looking at these lunar cycles at the moment. I know people they're going out at 3 in the morning and watching the moon rise, which is a lovely thing to do, I'm sure, you know, but looking along the line of the stones, not necessarily in the winter because it's blooming freezing, but yeah, but that hopefully gives you a little bit of context about Stonehenge. But more what I wanted to say was to give you a sense of the, I guess, the scale and the blend of different lithologies that are present at the site. Okay, so now what I want to do is I want to move on a bit and talk a little about the work that we've done on the sarsen megaliths. So I guess from the introduction, it was mentioned I've done a fair bit of work on silkrete over the years, and much of that's been in Botswana. And as part of that work would have been round about, it's about 15 years or so ago, I met a Middle Stone Age archaeologist who works out in Botswana called Sheila Coulson. And she got me working at one site in a World Heritage site where a lot of the stone tools that are found there were made from silkrete. So the same material as sarsen, that's the kind of the international name for sarsen is silkrete. But at that particular site, there wasn't any silkrete for a good 100 kilometers in any direction. And we spoke about it, and she said, well, do you think you could use chemical evidence to figure out whereabouts people were getting stone from? So we got some pilot money, and we basically developed a technique that would allow you to chemically fingerprint stones in the rock outcrops in the natural environment, and then do the same analyses on stone tools, or at least chippings from stone tools, and be able to figure out whereabouts people were getting stone from. And it was really building from that work. We published our first paper on this 2013. And not long after that, I got in touch with Tim Darvill, who you might have mentioned, who's one of the two people, along with Mike Parker Pearson, who you may have heard of, who do a lot of the work on Stonehenge. Sadly, Tim died at the end of last year. But we thought, well, can we have a go at applying this approach to see if we can figure out whereabouts the sarsens at Stonehenge came from. And we tried a couple of grants, trying a few grant applications, and in the end we got money from the British Academy to do some work, and that's what I'm going to talk about now, and then I'll talk a little bit about the controversies around this work a bit later on. So, pictures, that's my colleague Jake Chiborowski on the right-hand side, who's a fantastic geochemist. Now, what is worth saying to start with is when we started this project, we weren't actually planning to figure out whereabouts the sarsen stones at Stonehenge came from. That wasn't our original goal. What we were originally interested in doing was seeing if we could look at the chemistry of the stones and look at the chemistry of little fragments of sarsen that have been excavated at Stonehenge to see if we could figure out, could we match the little chippings to the original stones, and then we could figure out whereabouts some of these stones had been tidied up on site. So much more modest, actually, than we eventually ended up doing. But to do that, we still needed to do one first step, which was to try to kind of characterise the chemistry of the sarsen stones at Stonehenge. So we did this using a device called a portable X-ray fluorescent spectrometer. That's this little yellow ray gun, and it is basically a bit like a sci-fi ray gun. It fires an X-ray at the rock surface, and that gives you back a reading of a range of chemical elements that are present within the stone. So we analysed all 52 of the stones. We took 5 readings per stone at points across the surface where there weren't lichen, because lichen can interfere with the signal. And we did that over several shifts. I mean, the interesting thing about working at Stonehenge is you've got to work there when it's not open to the public, because it's quite a big money earner for English Heritage. It's their most important of all of their sites in terms of revenue. And people don't like people with hard hats wandering around in their Instagram photos particularly. So much of the work we did was in the dark, which is a really interesting experience, being in the middle of Stonehenge on your own, because I had to do one night on my own, in the pitch black, in the middle of winter, with a ray gun and a head torch. Aside from being very, very cold, it's seriously creepy, I think, is the best thing I would say about it. I mean, I can talk about asides here briefly. I mean, I did have one occasion where I was there and I had my ray gun and somebody walked up to me. I didn't see them walk up because they were all dressed in black and wearing a black balaclava and had a gun and said, "Everything going all right?" And you're like, and I'm trying to do a reading. And it's like, "Oh, okay, yes." And he was the rabbit shooter. So they employ people to stop rabbits burrowing into the site. Little things you learn about Stonehenge while you're working there. But we did 3 night shifts, and then these photographs are from one morning when English Heritage, who were fantastic, I will say, provided us with a mobile scaffold tower for free, which was amazing. But they sold it on the argument that they could then get their engineer up there to look at the state of the lintel stones, and they did discover some cracks and things that needed patching up and so on. So we got access to the stones, and genuinely like a life moment, you know, peering over the top of a lintel stone at sunrise at Stonehenge, absolutely amazing. But what we ended up with was 260 data points, which is a decent sized data set. Now I'm going to show a few wiggly lines and a couple of graphs, so I apologise, but I'll try to explain them. We then had to do some statistics on them. So I'm not going to go into the detail too much of the statistics. I have to say big thank you to my colleague, Georgios Maniatis, who's an absolute geostatistical wizard who did a lot of the stats work. But what we did was we tried 2 different statistical approaches. Now, what we were trying to do here, we used these chemical analyses to see if it would help us figure out how many sources of stone there might have been supplying Stonehenge. So the idea would be, we look at the data and see how they cluster. If we get one cluster, it suggests that there might be one dominant source. If we get 2 clusters of data, it suggests maybe there's 2 different sources. And we tried a couple of different techniques, and I won't, go into the maths of it all, but the first one on the left is a technique called linear discriminant analysis, which is really, it's not a super powerful statistical method, but it's really good for identifying initial clusters. And when we ran the samples through, or ran the data through linear discriminant analysis, you find that they all cluster quite tightly together with a number of outliers. But that line shows what's called the 95% statistical confidence limit. And what we find is the majority of our readings fall within that cluster. So from this, we could tell we were probably looking at one dominant source in this area. Some stones don't fall within that cluster. Now, the way we've looked at this, we've basically said if even one reading from a stone falls within the cluster, there's probably a link for the geology of that stone to that cluster. So if the readings all fell outside, we could say they were different. And we pick up here 3 different stones that from this initial exploratory stats appear to be different. We then tried a different technique, which is a much more powerful statistical method called principal components analysis. We used a particular technique called Bayesian PCA. I don't want to worry about the detail, but it's really good for data sets where you've got lots of values relatively close to 0, because these materials are mainly silica with small amounts of other things, and a lot of standard stats tests don't work very well on that kind of data. But we find a similar pattern, an even tighter cluster, and in this case, only 2 of those stones falling outside. And the interesting thing about this is, so we've probably got one main source as the take-home message, a few outliers, but we've got 2 stones that are different both to that main source, but also to each other. So within the limits of the data, what this is probably saying is that we're looking at, I guess, 3 main sources from this evidence for Stonehenge, one dominant one, and then a couple of smaller ones. But that at least gave us a path to then go ahead and try to see, what explorations we could do to figure out more about where that source was. So that's I guess, that's sort of the work we actually did directly at Stonehenge. Now, we were in the middle of analysing the data. We were literally in the middle of doing all these statistical analyses and talking to one another about what it all meant when, oh yes, sorry, forget a thing. I always do this with PowerPoint. I've highlighted stone number 58 here with a circle. So stone number 58 is shown with these little red triangles. And I think the important thing to remember about this stone is it sits right in the middle of those statistical clusters. So arguably it's pretty representative chemically of that main cluster. That's quite an important thing because you'll see where that feeds through in a little bit. So yeah, take home message, one dominant source, and remember the key thing being stone number 58. So we're doing these statistical analyses, and in the middle of doing that, I received an email from English Heritage. And it's always a bit alarming when you receive an email from English Heritage. I was asked, are you working at Stonehenge at the moment? And my immediate reaction was, oh my God, what have we done wrong? Yeah, but actually they were saying, well, we've been contacted by someone in the States. You may have heard this story. It was on the news at the time. We've been contacted by somebody in the States whose father has a core from Stonehenge. Would you be interested in having a look at it? Now, I almost bit their hand off because this is a chance. All of our work had been done on the outside of the stone. And the problem with that is that stone is weathered and there'll be a little bit of chemical alteration as a result of weathering. If you can get access to material from the inside of one of the stones, it opens up a whole range of other things that you can do in terms of analysis. So I was asked, well, would it be useful? And I was asked to write a kind of a little case for getting the material, getting the core returned to Britain, which eventually it did. But this core itself has got this is where I'm going to see if this video works in a second. This core has got, it's a lovely story around it if you haven't heard it. But Stonehenge that we see today, you have to remember, is the end product of obviously lots of natural processes, but also quite a lot of human interference with the site. So if you look at photographs from the early 1900s, you'll see Stonehenge with a lot more of the stones are on the floor. There's ones propped up with bits of wood. It really looks a bit sad. And there was a big effort in the 1950s to do lots of conservation work to try to make the monument a bit more understandable to the public, to make it look a bit more like it would have done when it was originally constructed. And there was all sorts of work. I'll talk a bit more about work on the altar stone a little bit later on. But one of the things they wanted to do was to erect one of the trilithons which had fallen over, and I'm going to check my dates, in 1797, when an archaeologist had dug next to the stone undermined it, and the whole lot came down. Oops, you wouldn't want to be that person, would you really? But they basically decided, let's re-erect, and this is stone 57, 58, and it's lintel. Now, during the course of that process, they obviously did inspection of the stone to check it wasn't damaged when it fell, and identified that stone number 58 had a crack running through its length. And they were a bit worried that if they erected it, it might fall down and it might injure somebody. So they decided, as you would do in 1958, that they were going to drill holes through the stone and pin it like you would do with a wall on a house. I mean, conservationists today like look in horror when you suggest anything like that, but that's what they did. They raised the stone and then they drilled through it in 3 places horizontally, put rods through, put bolts in, capped the holes with more sarsen that they found lying around, and left it at that. Now, the drilling work was done by a company from Basingstoke called Van Mops, who are still going. They're a diamond cutting company, and they were invited to do the drilling work, and you can see the drilling work going on here. There's the drill going into the stone. The guy on the left here, the gentleman on the left, is a guy called Robert Phillips, and wearing a nice suit welly combination, which is something that I aspire to. But he was the man who had the core who lived in the States. So basically, when they finished this drilling work, the ministry that was in charge of the conservation effort, which was the Ministry of Works at the time, gave one of these cores to the company. So they gave one of these cores in a perspex tube to the company. And Robert Phillips looked after it. And it hung on his office wall. He retired in 1976. As part of his retirement gift, they gave him the core to take away with it, because presumably they didn't know what else to do with it. They gave it to him. I'll show you, there was also a watercolour painted of the works as well, because Van Mops were very proud of all of this. Phillips was given the watercolour. He moved to the States. He moved around 3 places. And in the end, he ended up in Florida, and that's whereabouts the message came from about this particular core. Now, we uncovered, and I'll come back to what we did with the core in a second, but I think this is actually quite a nice little thing. This would be about 2-3 years ago. So I've been in contact with his son ever since this work. We call this core the Phillips core after his dad, after Mr. Phillips. So Lewis Phillips got in touch with me because Mr. Phillips, there's all these Mr. Phillips. Robert Phillips died about 3 years ago. He was in his 90s. And one of his sons went across to Florida to part clear his house out. During the course of clearing his house out, they discovered, I think they were 6, are there Super 8 films? Was it Super 8 or Super 7? It's Super 8, isn't it? Yeah. Some of which were family holiday films, but there were 3 of them that were marked Stonehenge. And they're amazing, I have to say. And I'm going to show one of them. So he contacted me, and at University of Brighton, we've got an archive called Screen Archive South East, who basically paid for these films to be restored and digitized. And they're now sitting on the website. So you can look at the other 2, just search Stonehenge drilling. It's a Robert Phillips collection, and they're digitizing the other films because they're quite a nice little picture of family life in the 1950s. So, but I'll just show if I can do this. Let's see how this works. This is where it'll all go horribly wrong. What I need to do, if I can, now for some reason, I told you it would go horribly wrong. I can't get my mouse to work. Let's hit escape. Let's try that. And then let's go into the web. That's working, and let's get the film going. Now, can I make this full screen is my next question. Yes. How's that? So this is from Robert Phillips. Now, this is a film that we don't know quite why it was made, but quite clearly it's partly staged. So it's not purely a random bit of film clip. I think it was made by Robert Phillips on behalf of Van Mops. But you can see there's the heel stones. This is back in the day when the road went right past Stonehenge. And you can see the green van. I love it because it's actually very of its time, this film. So there's the drilling rig, and I love the fact that there's this hierarchy of overalls. I'm not old enough to know about this hierarchy of overalls, and what the difference is between a brown overall and a white one. Somebody can tell me that. I'm sure it looks to me like the brown ones are mainly more engineering operatives, and the white ones are a bit more sciencey. There's a clear, there's there's a caste system here, isn't there, in terms of overalls. But you can see, it's only about 4 minutes, so I'll just show the whole thing. But you can see now, and I do love this because it's very much of its time, a lot of this film. But there's the stone, they've raised it. I love the fact that, you know, there's kids wandering around and people with their dogs, and a little picket fence. Nowadays, you wouldn't get near it if they were doing something like this, would you? But this is, they basically raised a pile of pallets, I love this, to get high up on the stone, hoisted the drill up, and then you can start to see the drilling. And it's amazing what they actually did. So we'll just keep going. There's bits in a moment that would make any archaeologist wince, like now. So you can see they've marked a circle on the stone where they're going to put the drill in. And off it goes, and in a second they'll start the drilling process. Here we are. So there's water jetting out of the drill, so it's a water-cooled drill, and then, ouch, in goes the drill. And this is them kind of pulling the core out, but you see all sorts of then hammering it through and poking out the other side. So the cores, we know, went right the way through, and here it is. You can see the core comes out. It's partly in pieces. That's partly the natural cracks in the stone, but you can see this is now starting to drill other ones. You get the idea, I think, don't you? But it's amazing that this film clip existed and it was just in a box in someone's house in Florida. Let's keep going. Now, somebody did tell me who the gentleman on the right was, who I've forgotten, who is quite a famous archaeologist. But I do love the fact that people are just standing there looking, and we're having a wander. It's good for fashion as well, isn't it? 1950s fashion, if you like that kind of thing. But let's just keep watching. So you can see the pallets there. It's just, isn't it amazing? People in suits on step ladders. It's kind of very much, yeah, woman standing at the back just watching. It's very much of its time, isn't it, I think? But there you are. You can see that's the drill coming out the back of the stone. You see the damage it did to the surface of the stone, which is, yeah, quite horrifying. But those are the 3 cores that they took out. We've got one of them. We've got the one at the back. We got access to the one at the back of the 3 that's a little bit more brown stained. This process shows how they then embedded the sarsen plugs that they used. So having drilled the hole out, they then drilled a wider hole so they could put the rods through and then put the bolt and then plug it with a bit more sarsen. Yeah, and that's, I think we're getting towards the end of it now. But you know, I just thought I'd show that because I think it's just one of these. It's a lovely bit of historical film of this work. So that's another one. The plugs coming out at the back. I'd love to know where all this stuff is because it's got to be somewhere, you know. But we've managed to relocate a part of the second core. That was found at Salisbury Museum in a drawer. But we don't know whereabouts the third core or the rest of the second core is. But you can see the holes, you can see positions where they've plugged up at the top there. And I think that's pretty much just about the end almost. Let's see how we go. Yeah, then we're looking right the way through the hole. I can't imagine they would never do anything like this today, where you can see people right the way through. Yeah, so can I pop the lights up a tiny bit so I can just see what I'm doing there? But hopefully that's, you know, you can watch that again. You can watch that at your leisure. So it's on Screen Archive Southeast, should you wish to watch that again. Okay, so that's the little film. There's the watercolour that Van Mops did of it. So they were really chuffed about this. It featured in loads of their publicity brochures, as you probably would do, I'd have thought. So what we did, so the core came back to the UK in 2018, and those are 2 of Robert Phillips' sons handing the core over to Heather Sabir, who's the chief curator at Stonehenge. And then we were able to give them permission to basically analyse the core. So there's my colleague Jake again in the top right using the same portable X-ray instrument. There's me wearing black rubber gloves, looking at a section of the core. And I think the thing that struck me about this core is its colour, because it's incredibly white compared to we always think of Stonehenge being, you know, grey and weathered. The core itself is this creamy white colour. And I always think it must have been absolutely amazing that when Stonehenge was constructed, so all of the stones were dressed, they all had their surfaces cleaned up when they were built. Must have been absolutely amazing to see this kind of coming through Salisbury Plain and then seeing this gleaming white monument. And the bluestones were probably quite fresh and purple coloured. Must have been a phenomenal thing to, to see that, and the power that would have had, and the shock that people would have seen must have been absolutely amazing. Now onto some data. I'm conscious of time. Onto some data. So we did some analyses of the core itself, and I'll just show a couple of things. So we did some fairly standard stuff. We did some sedimentary logging. So the core is just over 1 metre long. It's 108 centimetres long. We looked at things like the grain size variability, standard stuff you would do as a geologist. It's really boring, I think, is a polite way to say. So basically, much of the sand in the sarsen is kind of medium sand size. There's the odd little layer where it gets to coarse sand size, but it's really very, very homogeneous. Bit of colour variation. We did some portable XRF, and that's also incredibly homogeneous. The only thing that varies, so what we've got here are zirconium levels, we've got silica over on the right. The only things that really vary were iron, and that tends to be where you get iron staining that we mark on here. But otherwise, it's really very dull and very uniform. I think that's probably a better way of putting it, isn't it? It's very homogeneous rather than being dull. Then we got access. So we were actually, the thing that we got really excited about, we spoke to English Heritage while we were looking at this, and we asked, would it be possible to sample this core? I'm thinking like they're going to say, not on your life. But we were given permission to analyse that little fragment. So the core was in 6 pieces marked by the little break lines. We were given permission to analyse a 7 centimetre long bit, which looks like that. And basically what we did was we, at University of Bristol, cut that piece of core in half lengthways. English Heritage keep 1/2 for their archive. We were able to analyse the second. And obviously this was a really precious bit of stone to us, so we wanted to get as much out of it as we physically could. So we cut it into 3 subsamples. We cut the top off those samples for chemical analysis. We made thin sections from the rest. We made 2 sets of thin sections from the other material. And then we also had some off chippings that we did some isotope work on. Basically to try to get as much info out of this particular sample as we possibly could. And I say we, I'll show at the end, it was quite a team of us. A thin section, not sure if you looked at rocks under the microscope, people here will have done at length. It's really boring, this particular stone. I've looked at an awful lot of sarsen stones in my life, and this one's got to be up there as one of the more dull ones. But that's a good thing because it's incredibly homogeneous. And basically what it is lots of quartz grains cemented together by more quartz. And you can see that under plain polarized light at the top here and under cross polarized light at the bottom. This is just a zoomed out version to show just how uniform the cement is. This is some close-ups. And what you can basically see, I'm not sure whether you can see that little area there. There's like a little ghost of a sand grain in there. And what this basically is lots and lots of quartz sand grains cemented together by what are called overgrowths of quartz that kind of form an interlocking mosaic of quartz crystals. And that's effectively what most of the rock is. It's this really tight meshed interlocking mosaic of quartz crystals. So we looked at it under the microscope in various ways. We used a device called QuemScan. Now this is a really very nice piece of kit that does automated mineralogy. So what you do is you put one of your little thin sections into the device and it scans it, it does chemical analyses, and then it maps out where different minerals are, which is an amazing thing because normally you would have done that by painstaking inspection of thin sections. It's automated now. But I just picked this little part of one of the slides. So that's a millimeter scale down there. The yellow is all the quartz, so it's dominantly quartz. But what you start to see is little pockets of other minerals. So there's little titanium oxides, there's minerals like staurolite, kyanite, a little bit of tourmaline, all sorts of other minerals. And what the ChemScan showed is that this rock is 99.5% silica. It's incredibly pure, but it's the 0.5% that's the really interesting bit. And it's that bit that we focused on for the rest of our analyses. Now, the bit that we really focus on, and what I'm going to talk a bit more about, is some of the chemical data. So you remember I said we cut the sample into three, we cut the tops off. Those three little top bits we then used for much more high precision chemical analysis. And we used a device called ICP-MS, which is inductively coupled plasma mass spectrometry. And we used analyses using ICP-MS to construct what you might think of as the geochemical fingerprint of Stonehenge. Now that sounds very grand. All it is a wiggly line, actually. But I'll show you now how we constructed it. So what we did, we chose 21 chemical elements that are largely immobile in nature. So these aren't ones that would wash in and out of the sample. They're ones that kind of, once they're in there in minerals, they're not particularly mobile. And we plotted these. We divided the values through by zirconium. Don't need to worry about why. It's more to remove the effects of variable amounts of cement present in different samples. And you get a plot like this. Now, I guess you kind of have to trust me that that's actually pretty good agreement between those three readings. There's only a bit of variability in levels I can't see now. I think it's rubidium and yttrium over there. Is it terbium? Yttrium over there. Little bit of variability, but what that showed us was this is a pretty uniform bit of rock. And what we then did, we took the median value of those three readings and we added a small amount for instrumental error. So that's the little error bars on either side to allow for, we analyze standards at the same time, and you can work out how accurate your instrument is at detecting different elements. You can add a small amount of error. And basically that at the bottom left is the Stonehenge geochemical fingerprint. Very impressive, isn't it? No. Okay. Yeah, but that's what we're aiming for. Now, what we now had, having got that, which was really, we wouldn't have been able to get that without access to this core, we could now set about to sample sites in southern Britain to see if we could find natural sarsen areas that have the same fingerprint. And this basically is just like detective work. You generate your geochemical fingerprint and then you try to see if rocks in certain areas have the same fingerprint. So we set out sampling sarsens. Now sarsens occur right across southern Britain, and this map's a bit misleading because each blob indicates at least one sarsen. So it could also be clusters. So it looks like there's an awful lot in some places, but actually it's single stones and isolated stones. I'm not sure where we are at the moment. We must be kind of in there, are we, broadly? Yeah? So you're on the edge of the pudding stone area, but you're in the sarsen area, yeah? So there are sarsens all over the place. There's plenty around Brighton. There's dots along the south coast, but the big cluster is in the Marlborough Downs. There's Stonehenge a little bit further south. And they typically form on plateau surfaces, you find them, like here, but in the Marlborough Downs area, probably the most impressive spreads of sarsens are in valley bottoms, and they would originally have been probably not a continuous cover higher up in the landscape, but pockets of sarsen that then, as those valleys have eroded, have kind of rafted their way down into the bottom of the valleys, mainly by periglacial processes, it's argued, and they end up in the sites that we see today. So we set about sampling these, and we could have sampled an awful lot more. That's one criticism I'd very much raise against our work. There's Jake again. But we ended up deciding that we were going to target 20 areas. We deliberately didn't sample areas where there were large numbers of pudding stones because there aren't pudding stones at Stonehenge. There's one stone that's got a few flints in the top of it, but there aren't. So it's almost pointless sampling pudding stone areas. But we sampled from Devon up to Norfolk. We did 6 sites in the Marlborough Downs, but these are all some of the really big spreads of sarsens to see if we could characterise them. 3 samples per site, so we're dealing with, again, you want to critique this, we're not dealing with masses of data to characterise each site, but we were limited by the grant funding that we had. But we ended up collecting 60-odd analyses, which we could then do exactly the same thing with and try to compare them against the Stonehenge fingerprint. Now I'm going to show this diagram. This is awful, I apologise, it's really small. But what I wanted to do was just to show you the data set as a whole for all of our 20 sites in one go. And on these graphics, just to explain what they show, the black line with the little error bars is the Stonehenge fingerprint that I've shown you a moment ago. The pink band is the kind of range of chemical variability within each of our source areas. So that's kind of taking into account our error bars and our readings from a maximum and minimum values of each of our 21 different elements across the bottom here. And basically, the argument is that if the black line overlaps completely with the red zone or the pink zone there within error, so bear in mind there's a little bit of instrumental error, then you're dealing with a direct match. Now, we didn't think we would get a direct match from this because we knew that we hadn't sampled, absolutely everywhere. But you'll see straight away some sites just really clearly are not the same mix of chemical elements. So some of them are all over the place, some of them are much lower, some of them are a little bit higher. But if I zoom in on the 6 sites in Wiltshire, these are the 6 sites. These are some of the really big areas of sarsen in the Marlborough Downs. You can spot that. You can see how they're out. Even these ones, some of them are higher or lower. The only one that made a perfect match, and it's within error, I would say, that error bar there, which is for uranium. The error bar is just touching the pink zone. It's just inside it, and we argue that, and that was a site called West Woods, and it's basically through this process that we come to the conclusion that Stone 58 provides a direct chemical match with West Woods, and therefore, on the basis of those statistical analyses we did earlier on from the whole monument, because Stone 58 is representative of the chemistry of the main source of the main cluster of sarsens at Stonehenge, then by inference, West Woods is likely to be the main source for the majority of the monument. That sort of makes sense? Yeah, so that's really the journey that we came through. We still don't know. There's 2 stones that we don't know about. So I forgot what they are. Stone 26 and 160, I think they are off the top of my head. One of the uprights, one of the lintel stones. We probably never will because we're not going to ever get permission to core those. English heritage are there's not a chance that that's going to happen in my lifetime, I wouldn't have thought. But at least what we think we've got, and notice I'm being quite cagey here, I'm saying likely, likely source on the basis of the evidence that we have. It's likely that West Woods is the key site. So what's exciting about West Woods? Aside from the fact, if you go there, you go there at the right time of year, it's got the most amazing bluebells. It's a fantastic bluebell woodland. So if you like sarsens and bluebells, which I do, but we have plenty of bluebells at home, but not with lots of nice sarsens in there. It's well worth a visit. But it's an interesting site. It's one that's been overlooked by archaeologists. So most of the people who'd thought about, the long-standing argument about the sarsens of Stonehenge was they must be local because they're so big, people wouldn't have moved them a long way. And so people tended to look a bit further north. They looked at the big sarsen trains, like at Clatford Bottom and places like that. Nobody really looked in West Woods, partly because it's very forested, I suspect. It's not obvious where all the sarsens are. But in actual fact, West Woods, so this is just south west of Marlborough. It's got all manner of Neolithic archaeology in there. There's a very, very impressive chambered long barrow, huge structure there. There's standing stones. There's a polissoir, which is a sarsen which was used for polishing axe heads. There's prehistoric field patterns that probably postdate the Neolithic, but this was obviously a place that probably, at the time that Stonehenge was being built, probably wasn't wooded. It would have been a network of fields, and you probably would have been able to see the sarsens as you see them in other parts at the present day. So it's a site. It also has the advantage, it's on a plateau top, so you can see that on here. It's kind of on a plateau surface. It's south of the River Kennet, so you haven't got to drag the stones across a river. All the other sites that people have looked at have been up here. The original idea was probably they were moved to Avebury and then round through this gap. But you've got a high surface. You don't have to lug the stones over this big plateau surface. So it's a kind of an interesting idea. Maybe it's also the closest site with big spreads of sarsens as well. So it might be a relatively pragmatic choice of sites. There might be other symbolic reasons for going there. But what does it tell us? And I'll just wrap up. I'm talking for longer than I planned to now. I'm realizing this. I'm getting into the flow, and I apologize. But what does it tell us? I think what it tells us probably, as I say, is that West Woods was probably an important place, but we don't know quite how important it was. What it also probably tells us is a little bit about how Stonehenge was constructed, because if you think, if most of the stones are coming from one source, and we know, that kind of reinforces the idea that they were probably all put up at around about the same time. So you might have a concerted effort to move stones in from one place, which must have been amazing if you're moving 50 plus sarsens through the landscape into Stonehenge. But it might kind of reinforce this idea that the monument was constructed in a relatively short, I say relatively, decades kind of period of time, that kind of scale. It might well support that. And it also lets us start thinking about routeways, because most of the problem in the past has been we haven't got a starting point for planning a route. Now we've at least got an area that we can start from. So early ideas, as the archaeologist Atkinson was the one who suggested that probably the sarsens moved from the Avebury area round through this gap and then down southwards. Archaeologist called Hill in the 1960s suggested a route down the River Avon. We kind of favour a route slightly further west. I mean, it's difficult. There's no evidence exactly for why this might be, but this route takes in a few Neolithic archaeological sites. And I'm kind of the view that why would you take the least effort? If you're going to move 80 blooming great big boulders 15 miles, why would you bother about taking the least effort route? You'd probably parade them, wouldn't you, in some way? And you might move them through other important places. But at least it gives us some possible ways to start thinking about routeways. Right, quickly then. Controversies. I've sort of touched on a few things, and it was actually quite quiet for about 3 years after the paper was published. So we published this work in 2020 and didn't really hear very much critique, a little bit. And then people start, I guess it takes a bit of a while for people to digest things, but there's a really interesting critique of the work. If you ever want to read a really, really good book, Mike Pitt's book called How to Build Stonehenge is absolutely fantastic. It's very much public archaeology, and it kind of talks about, literally that. How would you build Stonehenge, starting from where would you get stones from through to how on earth would you build it? And Mike's got some really interesting critiques in there, and I've talked to him about it, and I agree with him absolutely 100%. But what he said, for example, we've only analysed 20 potential source areas, so an obvious criticism is, well, what might you find if you sampled more? And we don't know. We're lucky that we found one that's an absolute perfect match. It may be that we find others. I kind of doubt we will, but it may be that we find others. There's a critique that only 6 sites were sampled in the Marlborough Downs. Why not more? Yeah, that's a money issue largely. The big one is none were on Salisbury Plain. So there's been a long-standing idea that the sarsens weren't moved to Stonehenge. They were already there, and then they were just built. And then people also critique the number of samples, but again, that's a financial thing. Now, in response, I've thought quite a lot about this since Mike he contacted me about it and said, I'm going to publish this, am I being fair on this? And I was like, yeah, you are, absolutely, it's absolutely fine. Having thought about this, I mean, I'm personally, from the geological evidence, doubt that there were ever really big spreads of sarsen boulders with the same geochemistry as West Woods. That's quite a key thing. There may have been sarsen boulders, but whether they had the same chemistry as West Woods actually on Salisbury Plain. And the reason I say that is because you'd need a real, quite, unlikely alignment of a number of geochemical factors and geological factors to get sarsens with exactly the same chemistry as West Woods 15 miles away on Salisbury Plain. I won't go into detail, but you'd need thick sandy sediments of the right age across Salisbury Plain. Probably not the case. There were certainly sediments of Paleogene age across Salisbury Plain, but not really necessarily that sandy from the evidence that's remaining. They wouldn't want too much clay, because to develop those lovely overgrowths that I showed, you don't want much dirt and mess in amongst your sand grains. You want it to be really clean. You'd need a structure like a syncline to allow groundwater to focus in and cement those stones. And there's very little evidence that there's any major synclinal structures. And I think the killer blow for me is you'd need to have exactly the same mineralogy in those sands as you do at West Woods. And I don't think that that's the case. So I'm sure there's other people will come along and critique, but that's where we are with the sarsens. Now I'm checking how we're doing for time. Have I got? Am I allowed about another? You cope with 10 minutes? I know people have got homes to go to. I have a home to go to as well later on. But I just want to talk through a little bit about the altar stone. And I've only got literally half a dozen slides about this, so I'm not gonna go on for too long. But I thought I might talk about this because it's quite interesting in that this is something that really made the news last year, and you probably saw this on the news about the idea that the altar stone may well have come from northeast Scotland, which, if it's true, is an absolutely amazing finding and really does throw things up in the air about Stonehenge. Now, bit of context, and I don't like this. Difficult. This I don't like necessarily talking about other people's work. I'm much more comfortable talking about my own. I don't like critiquing other people's work. I'm happy critiquing my own. So these are my views. Yeah. So I'm just going to caveat it by sort of saying that. But the altar stone's has been the subject of interest for quite a long while. So it's a sandstone. It's there are other sandstones at Stonehenge, but it's the one that's right in the middle of the monument. It's also one that's really quite difficult to analyse because it's sitting underneath two fallen sarsen stones. So the stone there, I think, is stone number 55, which has fallen over and broken in half. That's its lintel stone there. So it's kind of buried underneath. There it is. This is what it looks like. So you can just about make out a bit of it there and a bit under this stone here. This is from 1958, when, as well as doing the re-erection of the sarsens, they also did quite a lot of digging and excavated around the altar stone. So you can see it's kind of, I'm not sure about the size of it. It's about 3.5, 4 meters long, and it's a kind of oblong slab of a micaceous, slightly green sandstone. We don't know whether it was standing up in the past or whether it was laying down. There's no clear way of knowing that because they haven't found base holes for the stone. But as you can see from here, it's sitting right in the middle of the monument. It clearly was quite an important stone as part of the construction of Stonehenge. Now, it's worth saying, excuse the small print here, compared to our work, so we started almost with a clean slate on the sarsens. Nobody had really ever done any proper work on whereabouts the sarsens came from. So we were kind of starting from not very much. The altar stone has had a ton of work done on it, and it's been very incremental. So there's people like Rob Ixer, Richard Bevins in particular, that have done lots of smaller studies building up information about where the altar stone might come from. And I've kind of plotted it as a bit of a timeline here for you. But I guess the picture, at the end of the 20th century, it sounds like we're talking a long while ago then, doesn't it? It was only 25 years ago, but end of the 20th century, the prevailing idea was that probably the altar stone was picked up en route from the Preseli Hills to Stonehenge. And that idea has been around since the 1920s and the work of Thomas. Atkinson suggested it was probably from around Milford Haven area on the basis of I don't know what evidence, but that was the kind of idea. It must have been picked up en route with the other blue stones on their way to Stonehenge. And then there's been all sorts of studies. So people have looked at thin sections and said, well, it must come from the old red sandstone outcrop in South Wales in a particular layer of that called the Senni beds. And then there was other work that found excavations at Stonehenge had found sandstone fragments, and the suggestion was that, well, these fragments must be debitage, they've got to be debris knocked off the altar stone. And then people did analyses of those fragments and said, well, actually, it's probably got the closest match to the eastern end of this Senni beds outcrop. They were kind of honing in on South Wales as a possible source. Studies from the 2020 looked at the clay mineralogy of the altar stone and suggested it was probably from southeast rather than southwest Wales. Yeah, then we did more PXRF work like we'd done, but in this case, analysing the actual altar stone itself and looking at these fragments again and saying, well, these are probably the same materials. I'll critique that in a little moment, but linking them together. Then there was a paper that came out in 2023 saying, oh, it's got a very high barium content. It doesn't look like it's from the old red sandstone in Wales. We need to look a little bit wider afield. And then in 2024, lo and behold, I'm sure they already knew that they were looking further afield, me being cynical, but that was when the paper was published about the stones coming from the Orcadian Basin in northeast Scotland. So we've kind of gone, and there's other steps in between, but that's the kind of the journey. We've gone from South Wales now through to northeast Scotland as the likely source. The paper from 2024 is this one. You can look at it online. It's open access, fully available, called A Scottish Provenance for the Altar Stone of Stonehenge. It's quite a techie paper. So it's kind of a not for the light-hearted paper. But what I've tried to do on this next slide is summarise it in 4 bullet points. So I'll try and explain what they did, because it's different to how we did this. And I'll also enlarge those graphics in a moment as well. But basically what they did for this study, so we were looking at chemistry. In this case, they were looking at the ages of minerals within the stone. So they were looking in particular at 3 minerals, zircon, rutile and apatite, which are very resistant minerals, which you find in a load of sandstones. And they determined the ages of those individual zircons. Now, the ages of zircons, as an example, relate to, so they form within igneous rocks. Imagine you've got like a granite, like in Dartmoor. When that granite was still molten underground, it was still magma. It would all have been, all the chemistry and different elements would have been mixed together. Things start to crystallize out. Zircons, rutiles, and apatites crystallize out. And if you can figure out the age of the zircons, it gives you the age when the granite formed. So the little minerals record the age of magmatism, if you want to think of it in that way. And the idea then is that if those rocks are then eroded and the little zircons get washed out into sediments and those sediments become sedimentary rocks, you can then, if you look at the ages of your zircons within your sedimentary rock, there's potential to see how those age profiles compare with original rock sources. And in some cases, you might get more complex histories in an area. So you might find, for example, that there's an original, I don't know, an original granite, and then long while after it's formed, there may have been another magmatic event. It might be caused by mountain building or something. That then generates zircons of younger age. And then that whole landscape's being eroded. So your rocks might include a diagnostic mix of different ages of zircons, for example. And that's what they did. They basically looked at thin sections of the altar stone. They looked at thin sections of sandstones, and they compared the mix of zircon, rutile, and apatite ages. That sort of makes sense, broadly, I hope. I'll show some graphics that will hopefully make it clearer. But what they picked up from the zircons was that there were 2 main groups of ages of zircon present. One of them dated back to a period between 1 and 3.5 billion years ago. That's probably during that boring billion, I guess it is, pretty much, that you might hear about tomorrow night if you listen to that talk. These rocks were thought to be part of what's called the Laurentian area. They basically, this is an old landmass that was made up of crystalline igneous rocks, and a lot of those rocks were formed around about 1 to 3.5 billion years ago. And then also there was a signature from about 460 million years ago, which reflects a period of mountain building that was associated with the building of the Grampians in Scotland. So what you've got are these sandstones within the altars, the zircons within the altar stone, having this kind of bimodal, not quite, but bimodal signature of ages that suggest it's a mix of Laurentian and Grampian rocks that were eroded in order to form it. So what they then did was they then did these age comparisons. They got this profile, I'll show you it in a second, and then they compared it with sedimentary rocks across the UK and did something very similar to what we did. We used direct numerical matching. They do statistical matching, but they kind of see which age profiles match most closely with the altar stone and different areas around the country. The 2 main graphs they show are on the right, and I'll just enlarge these. So the left-hand one is a statistical technique called multi-dimensional scaling. Don't need to worry too much about the detail, but what it does is it looks at the data set of all these ages that are generated from the stones, and then it kind of pulls apart age clusters from different areas. And what this shows, basically, there's the altar stone, and it shows it has quite a strong overlap. It's very close to Laurentian signal, but it overlaps most strongly with the Orcadian Basin signal of ages. And you can see that also on the right-hand side. It's a bit more fiddly diagram, but this is showing what's called a cumulative probability curve. And it's a bit like you're looking to see which lines most closely match. And if you look at this, the altar stone, which is this kind of reddy orange, most closely matches the black line running through here. So on the basis of statistical similarity, that this is really where they've got the suggestion that the altar stone most likely comes from the Orcadian basin. It's basically by comparing the age profiles of zircons and rutiles and apatite within the rock with age profiles of other rocks in different parts of the British and Irish Isles. And it shows a bit more nicely on this graphic, actually, because that's the profile. So this is a bit more of a bit like a bar chart or a histogram, but smooth, so there are sort of peaks on it. This is the altar stone at the top. That's the record from the Orcadian basin, and you see there's this kind of double peak, which is this Laurentian zircon profile, and there's this bump down here, which is the Grampian profile, and matches up with that. You can see also it doesn't match several other basins, and they include loads of diagrams of these profiles from the other basins. Now, that's basically the story of how they did the matching. And hopefully that kind of makes loose sense. So it's statistical similarity between a zircon, rutile, apatite ages for the altar stone versus different areas. Now, if you read the paper, quickly, you'd be thinking, wow, and I did when I read this, I was like, wow, that's incredible. Then I read it in a bit more detail. I still thought, wow, that's incredible, but I started, I guess, probing a little bit more deeply into some of the things about what they've done. Some of them, and I'm gonna present this, I'm not gonna necessarily, make judgment about it, but there are some things in here where I wonder about the strength of the evidence that they've got. And I'm just going to pick out 3 issues. So number one, bit like our work, sampling issues very much come into this. They analysed 2 samples of what they argue were pieces of the altar stone. So these were pieces that were found in the National Museum of Wales from excavations and Salisbury Museum. They also the only new analysis of old red sandstone in this paper are 2 samples from Orkney and one from Caithness, both of which were bought from a shop in Whitby, which I found really intriguing. But there we are. So there's not actually any field work involved in this at all. Not a problem with that. I don't have any problem with that. But where you'll see in a moment, where it does cause some problems is you don't exactly know where it sits in the stratigraphy, where exactly your samples are from. Then they compare it against data from the Orcadian basin from a paper by Strachan et al. That's what produced the black wiggly line on that previous graphic. That's only from 5 samples of rock. So what you've got is a kind of quite a big story about Stonehenge based on analysis of 2 bits of altar stone and largely 7 samples of old red sandstone, 2 of which were bought from a shop. I won't emphasise that. But what this means, I mean, from my critique of this, I mean, if I was looking at this, no fieldwork undertaken, no problem with that, because a lot of studies use secondary data. But it does mean you don't have information about the stratigraphic context of your samples. More worrying for me is that these 7 samples are meant to be characterising the old red sandstone sequence in a big basin. And the old red sandstone sequence in Caithness is 4 kilometres thick. In Shetland, it might be nearly 8 kilometres thick. And you're trying to characterise that from 7 bits of rock. That's for the benefit of the Zoom viewers. I just went, okay. So that's my take on that. I think it's quite a big ask, and it's quite a big jump there for me to say I've characterised a basin on a fairly small number of samples. I'm moving on. The second thing are the zircon spectra themselves. So I've zoomed in now. I showed this part of the diagram before. There's the altar stone that's based on 2 samples. Here's the Orcadian basin that's based on 7. I delved into, because I was really interested in this, I went into the Strachan paper to try to see how variable those profiles were that are used to create this graphic. That's the same bit at the top there. So this is kind of a smoothed out version of that profile at the top there. But if you look at these 5 zircon profiles from their 5 different samples, which are scattered all over northeast Scotland, none of them match that. So this paper is basically, okay, claiming a match between the altar stone and zircon profiles that don't actually exist, if I'm being really harsh about it. Now, I'm not a zircon specialist, so I don't know whether this is conventional that in an area you combine your data sets to make one, but that struck me as being a bit odd personally, because what it means is there isn't actually a rock outcrop anywhere out there that they've sampled that actually matches the altar stone. At least we could say, well, we've got pieces of rock that chemically are, you know, indistinguishable from that rock over there. At least we could say that. Here, you don't have anything that directly matches. So again, that for me is a question. And then the final thing, which again, I started reading, because I was really interested in this. And it's one of those things, the more you read, I then sort of started to wonder, well, actually, are the samples they analysed from the altar stone actually from the altar stone? And if you look back, I mentioned there was the paper where in 2023, they used PXRF, so the same kind of ray gun that we used. They analysed some of these excavated fragments of altar stone. And then they also went into the field and did PXRF readings on the altar stone itself. And then they compare them to see, well, do these chippings come from the altar stone? And they claim that they do. They plot there's lots of different plots here. I've just picked a few out here. But I have to say, some elements work really, really well. There's really good agreement. I've listed a few here. That plot's beautiful. Yeah, so the red ones are the altar stone readings. The open bluey greeny symbols are the chippings that they analysed. That works really well. There's a really clear relationship, and you know, all of the different readings all fall on a straight line. That one's not bad either. There's a big spread, but they all kind of overlap. That one, goodness me, the reading up there for barium is absolutely distinct, barium and strontium, a completely distinct cluster to all of the other readings. Over here, this is the reading from this stone down at the bottom. That one's got much lower levels of iron than all the others. It's that same stone again. There's some real variability. And if I was looking at this, I wouldn't sit there and say these are the same stone, personally. I would look at it and say there's something odd going in here. I'd be trying to explain why there's high levels of strontium and low levels of barium. I'm not sure I would actually say that they are definitely from the same stone. So there's good agreement for some elements, bad agreement for others. Now, the worrying thing is that I've underlined the two stones. Those are the two samples that they use in the Clark et al. Paper, including this green one, which is really a bit iffy. And I haven't when I got to that point and I started thinking, well, I don't know whether these samples are even from the altar stone, and you've taken 7 analyses to characterize an entire 4-kilometre thick section. I'll leave it at that, I think. But I read this and I became really, I suppose, very, very critical of it. And if any of the authors are watching the Zoom video, I apologise. It's my personal view. It would be fantastic to have a chat, really, to find. I'd like to know a lot more about why you stack together your zircon profiles to make a profile for an area. I'd love to know why that's done. I'd love to know why you say that these stones are exactly the same thing. But there we are. So I'm going to wrap up there because it's now, God, it's 1:15. It's just I've been talking for far too long. What I've tried to do there, I've tried to just give you a bit of a snapshot. I think probably showing that video didn't help, but hopefully that was interesting. What I've tried to do there is at least talk you through, I guess, arguably they're two of the, you know, the I wouldn't say big breakthroughs because that sounds like I'm bigging myself up a lot, but they're certainly two of the bigger news stories that have come out about the stones at Stonehenge. And I guess what I've tried to do is to point out, you know, what are the issues with those? And from a personal perspective, I'd hold my hand up and say, with our work, we should have sampled a lot more. And we had lots of discussions about that where we actually said, well, can we even try to publish this work with this number of analyses? And we said, well, yes, because we've got a direct match. And you can't take away the fact you've got a direct match between a site. I guess time will tell if we find that there are other matches. And I guess it's going to be like any story, like the story about the altar stone. I'm sure that the more data we get, the more complicated it will get and the more complex the story will become. But I should shut up at that point because I have talked for far, far, far too long.